This is step 2, 2022, question 8. Um, this was the last question of the pure section of a not so easy paper, in my opinion. I did this paper earlier today, and I would say out of all of the recent papers, like I'm talking about like 2019 to 2023, I would include 2024, but I haven't sat that, and I've only heard about it from like other people, so I can't really judge that. So from 2019 to 2023, I would say this is probably the second hardest paper I've done. Um, in that in those years. And I would say the hardest is 2020. I'll go over some questions from that probably after this in the next video. And this is probably the second hardest. I would say the easiest is probably 2021, and the second easiest is 2023, by not by much so. But yeah, not an easy paper by any means. I only did the pure questions though. Didn't really go through the mechanics, but maybe I'll do that in a later stage. Who knows? Anyways, let's get into it. So, also another reason I wanted to do this question specific is because there's not enough really matrices questions in step two. It's like a new addition. So if you're preparing for step two, really try and nail these questions because they're usually not too hard. Like I don't really think this question is insane, but yeah, it's interesting. So yeah, let's get into it. So we have the matrix M, which is A, B, C, D, is a real matrix where A does not equal D, and the transformation represented by M has two distinct invariant lines through the origin. Okay, so the process of finding an invariant line, this is literally just core pure, the matrices chapter in core pure. So it'd just be like, or the linear transformations chapter in core pure 2. I don't know where it is. Anyways, it should be in core pure. Essentially, if we multiply this matrix by x and y, and we get something called big X and big Y, let's call it, where obviously the x's and the y's are different, but the line is the same. So the gradient, basically the line's going to map to itself. So the gradient and the y-intercept is not going to change, but the point will be different. The point on that line will be different. So what we can say is, well, let's multiply this out first. I mean, ax plus by is equal to x, big X, and cx plus dy is equal to big Y. Now, y just equals mx plus c, but c is just 0 here because it's from the origin, so we can discount c. And because the line's mapping to itself, then the gradient of big Y, or of the line we're mapping it to, will be the same. So big Y will just equal m big X, right? Where x is obviously varying, but m is the same because it's the same line, like I said. And we can substitute these values in. So ax plus bmx is equal to big X, and cx plus dmx is equal to mx. But we know big X is just this function small x here, so we can just rewrite it as this. And we take everything to the other side. I'm going to move to the left-hand side of the page, but if we take everything to the right-hand side, we'll get this. And we can take x common. Now, clearly x is not going to be 0, and if you just look at the kind of function they want us to talk about, we clearly need to consider this function of m to be 0. So, well, this quadratic. So if we take this to be 0, because x is not going to be 0, so this must be the only thing for this to be satisfied, therefore this function needs to be 0. We'll get this. Obviously factoring out m from this am minus dm term, and we get this. Quite an easy warm-up, like just, yeah, quite a nice warm-up. But yeah, quite chill. I think that's like, what, 5 marks easily bagged, so nice. I mean, the examiner report said that the only difficulty in this question was the first part of people forgetting how to do invariant lines, which is fair enough because, you know, it's not, at least I have not seen it in recent years come up, like this sort of chapter come up, so it's quite easy to forget. So I'm going to delete all of this, but keep this result here that we proved, because it doesn't really it's not relevant for the next few parts. But cool. Okay. Now it says if one invariant line is the y-axis, what is the gradient of the other? So let's think about this, right? If we have a point on the y-axis, we're essentially saying that the line, you know, the y-axis line or the line x equals 0 is not going to change. So x is constantly 0, so we can say this. We can say that this is true, okay? So therefore, b equals 0. If you just multiply it out, you're going to find that b is just 0. So now we can rewrite this as a0 or a0 cd times some, now because now we're considering the other line, x, we can just straight up just write this as mx and x mx, and we do the exact same thing we did earlier, but we'll be discounting the b term because it's 0, so it'll be ax equals x and cx plus dmx equals mx. Substitute the big X in, we get cx plus dmx is equal to max. I'm going to go to the left hand side, and we'll get, if we take everything to the right side of the equation, we'll get amx minus cx minus dmx. Take out an x, and we'll get, so this equals 0, am minus dm minus c equals 0. So again, we're going to just consider this function of m to be 0. So am minus dm minus c equals 0. Substitute m, we'll get this. I mean, I'm just making sure I've done everything right. Yeah, okay, cool. And we'll get a minus d equals c, and then m is equal to c over a minus d, which is, let me check if that is the correct answer. I think it is. Yes, that should be the right answer. Okay, wait, no, we've got it the other way around. Hold on 1 second. Unless I've done something wrong, which I don't think I have. A minus d over c. I think that's right. I think I'm not really looking at the mark scheme. I'm looking at the white paper. But I think that should be fine. Because they've gotten the same thing I've gotten, but the reciprocal. I'm gonna check the mark scheme actually. Sorry, 1 second. Okay, yeah, no, it's correct. Okay, I think that was just an error in the marks in the white paper. Okay, cool. It's all good. So that's part 1 done. Honestly, chill part, not too difficult. Quite a nice warm up, to be honest. Keep this result here, by the way. Okay, this will be important for the later parts of the question. Now, part 2, we want to show that if the angle between the two invariant lines is 45 degrees, then this holds true. Okay. So what we can do is, now let's think about this sort of case, right, of a line, of the line, right, and it starts in the origin, so we know it will look like something like this. Okay, this is 45 degrees. Now the mark scheme goes on to do something about vectors and stuff like that, but you really don't need to do that, at least in my opinion. There's a much more intuitive way to think about it, and I think it's a good rule of thumb is that whenever you have angles between lines or angles in anything, you should always think about tangents because you know what the gradients are, and we know that the gradient of any line is essentially the tangent of the angle that it subtends with that line subtends with the x-axis. So if we call this angle here beta and we call this big angle here alpha, then alpha minus beta is equal to 45 degrees. That's what this means, right? And if we take the tangents of both sides, we get tan alpha minus beta is equal to tangent 45, which is just 1. We get this, right? Now, we can use the tan subtraction formula, and we'll get and then rearranging, we get we get 1 plus tan alpha tan beta. Great. Okay. But we also know that the tangent of alpha and the tangent of beta are the gradients, are are m1 and m2 respectively, and we can get m1 and m2 by considering the roots of this equation up here. Okay. And how do we do that? Well, we have a quadratic, so the best sort of route to take would just be to consider the quadratic formula and pray something cancels. Um, so what we can do is, well, the quadratic formula is minus, what will be, in this case, will be this. Okay. And we can put m1 to equal tangent alpha, which will be the positive root or the largest root, and tangent beta, which will be m2, will be the smallest root to come out of this because we obviously need this angle to be great. We need this angle to be positive, therefore alpha needs to be greater than beta, therefore tangent alpha needs to be greater than tangent beta, and therefore m1 needs to be greater than m2. I think that's fairly obvious, but still worth explaining. We can bring this negative inside and we end up getting this. Cool. Now, if we just plug in tan alpha and tan beta and, just hope something cancels, we end up getting something like this. So tangent alpha minus tangent beta, which would be the m1 minus m2, will just end up being 2 root a minus t whole squared plus 4bc. I'm not really going to work out because it'll take up a lot of space on the page, but you can try it yourself. You'll see that it cancels because it'll just be the positive root minus the negative root, but the negatives will make a positive, and this will this term here will end up cancelling. How do I get rid of that? Yeah, it'll just end up cancelling, and will be equal 1 plus tangent alpha tangent beta. So tangent alpha times tangent beta will just be a difference of 2 squares, because if we just group this term here and this term here and this term here, that's horrible notation, I'm sorry, this term here, as like 2 different variables, we call this left term a, and we call the right term inside the square root, or even without the square root, b. It'll be a plus b times a minus b, which just ends up being a difference of 2 squares. So it'll be a squared minus b squared. So we'll get something like this, and obviously the squared of this term here will just take away the root. So we end up getting something like this. Again, it sounds like I'm waffling, but just try it yourself and you'll see what happens. So we get 1 plus d minus a squared minus a minus d whole squared plus 4bc. Yeah, I'm honestly being quite quick with it because I want to save space on the page and I don't want to go too far down, and then it will just look quite messy. But you got to be careful here, right? Oh, sorry, it's also over 4b squared. You got to be careful here, right? Because d minus a whole squared, you got to realize it's the same as a minus d whole squared. And if you don't believe me, or if you think that's wrong, literally just do 5 minus 4 or 5 minus 2 whole squared and do 2 minus 5 whole squared. It's the same thing because if you square a real number, it will always be positive. So it doesn't matter. So you can cancel out these two, and you're going to get. This should also be b over 2b. Cancel out the 2's, we can bring the 2 to the right hand side, and you get these 2 here will cancel, square both sides. Perfect. That's part 2 done. Honestly, I think just from that you've bagged, I think 12 marks, maybe 12, maybe 10. You've already bagged half the question really quickly, really easily. So yeah, honestly, again, this stuff just looks harder than it is. Usually the matrices chapter is quite simple, but I do think it's much more intuitive to think of like tangents, and because you already know what the gradients are instead of doing dot product and stuff. Although it might be quicker, I don't know. I haven't really checked. It might be quicker. It's just much more intuitive just to do tangents because that's what I'm used to doing whenever I see stuff like whenever I do like these geometrics or graph stuff and I see angles, I always think about gradients and tangents. But yeah, okay, cool. So we've proved this result. We can delete all of this. I'm going to keep this this quadratic up here though, because it does come in handy for part 3. So it says find a necessary and sufficient condition for A, B, C, and D for the 2 invariant lines to make equal angles with the line y equals x. Okay. Cool. Right. Okay. Let's again draw out the scenario. Always try and draw out the scenario if you can, because it will just make it easier to visualize. Because you know, it's a general scenario that at the end of the day, it doesn't matter how you draw these lines, as long as you label it properly. It's chill. So let's start from the origin. We have 2 lines, and in between is the line y equals x, and they subtend the same angle theta. Now you can immediately see like this line is a reflection. There are reflections, right, in the line y equals x. I think if you consider vectors, you could that would be a handy information to know. But you don't really need to care about if we're just taking angles and taking tangents. We don't really care about if it's a reflection or not. It doesn't really come handy. Or well, I guess it does a little bit because because this angle here is 90 minus alpha, and this angle here is beta. But yeah, we don't really consider reflections. We don't need to consider the reflection, but it's just a good thing to note. But yeah, if this angle here is beta, then we don't really care about these 2 thetas here. We only care about this angle here, which is 90 minus alpha, because obviously, like I said earlier, this angle here is alpha. Okay, so because well, actually, yeah, I guess you do need to consider the reflection now. Now that I think about it, because it is a reflection, beta equals 90 minus alpha. So if 90 minus alpha equals beta, then we can take the tangent to both sides, and we'll get. But we also know that tangent of 90 minus x, or tangent of pi on 2 minus x, is just the cotangent of x. But the cotangent is the reciprocal of tangent, so it will just be 1 over tangent alpha is equal to tangent beta, and therefore 1 equals tangent alpha tangent beta. And further, we know that tangent alpha and tangent beta are m1 and m2 respectively, therefore 1 equals m1, m2. And this is our first condition, okay? We go further. If you just do difference of 2 squares and stuff, you end up getting that 1 equals minus 4bc. But this doesn't really end up being helpful. I'm surprised it isn't. But yeah, it doesn't end up being helpful. But we got our first condition here, okay? Now there is one more condition, and I think this is the necessary one, or at least we've done the necessary one. I think this is the sufficient one. But and it comes from the roots of polynomials, right? If you look at this quadratic here, because what we've done, we've basically said that the product of the roots is 1, but we also know that in a quadratic, the product of the roots is equal to, in this case, minus c over b. So therefore, minus c over b equals 1, and therefore b equals minus c, and b plus c equals 0. So here is our necessary and sufficient condition. I guess this is the real condition we need, because this condition here that I've circled earlier leads us to this final condition. But okay, cool. So it says in part 4, give an example of a matrix which satisfies both conditions in part 2 and part 3. Okay, if we write out what we proved with the 45-degree angle in between thing, we got this. Great. Now we can use the fact that b equals minus c or c equals minus b to get this. And therefore a minus d whole squared is equal to 8b squared. Now, okay, what I did here is I literally just I just thought about this for a really long time and just thought what numbers would work, and I miraculously got to b equals root 2, a equals 5, and d equals 1, and that works. So then you just end up getting this, and that is your matrix, and that's it. That's the whole question done. I wonder if there's an easier way to do this final part. I'm sure you could just any numbers would work if you spent long enough on it. When I did this question to time, I didn't get this final condition here of b equals minus c, so I only ended up getting 15 out of 20. But I think those 15 marks are very, very accessible. The last 5, bit tricky, but you can get 15 out of 20 in this question fairly easily. Yeah, I forgot about this. I honestly forgot about this whole roots of polynomials thing. I only ended up with this condition here, so I was kind of stuck, and then you can't really get the final part of the question. But still, 15 marks. That part, this last part plus the last part of part 3 is only 5 marks, so it's not that detrimental. Let's go over the exam report just to see what that is saying. Large number of attempts at this question, but high scores were rare. Attempts are one of the major reasons for losing marks is a lack of understanding, where one invariant line is the y-axis and needs to be addressed separately. Okay, that's fair enough. That one did take me some time. Just I don't know why I just did. At least when I first did it. Part 1, many candidates solve a matrix equation to find invariant points rather than invariant lines. Okay, yeah, that just comes back to like remembering what an invariant line is. It's essentially an invariant point is when the point itself doesn't change, but the invariant line is when the line will not change. So think about it like the gradient is going to stay the same and the y-intercept will stay the same, but the point you can change your x-coordinate on that point. But the actual structure of the line, like the gradient and the y-intercept, will not change. It's invariant. So yeah, at least that helps me to kind of remember what it means. Another way, just think about it, is like if we have a point, right? An invariant line would be like if we had a point here, it would still, like, we can shift it here, or the x coordinate will change, right? But it's still on the same line, right? The point, like, I hope that makes sense. We can kind of, if we have like a point here and we just shift it down, up and down that line, it's still going to be on this line. The y coordinate is going to change, the x coordinate is going to change, but the line itself is not going to change, if you know what I mean. Or maybe I've just described an invariant line of points. Anyways, whatever. The gradient and the y-intercept stay the same. That's all you need to remember. Great. There are possible approaches to part 2 and part 3, the simplest of which involve the tangent addition formula. Addition formula? Okay, I use the subtraction formula, but anyways, you get the same result. Realization that the two lines are a reflection of one another. Yeah, I guess I said you didn't need to use it, but you kind of did, because that helps you realize that this angle here is 90 minus alpha, although that's quite obvious just by looking at it. However, many applicants do not appreciate that the angle between the invariant lines is not necessarily the same as the angle between the two vectors. Okay, I don't know about the vectors approach because I didn't take that approach. And they were able to find a suitable matrix. A very small number produced irrelevant calculations, but but failed to write. That's probably just a silly error because low-key you kind of do need to like. I think you need to do some guesswork here. But yeah, that was step two, 2022 question 8. Interesting question. Probably gonna do some 2020 step questions tomorrow if I can be asked or whenever I have time. But yeah, thanks for watching. Bye bye.